Okay. So in the last hour, we talked about Monte Carlo. So I'll assume that everybody understands a little bit about that. And now we're going to switch to quantum Monte Carlo. And the first technique that was developed, it was called Variational Monte Carlo. And it's only slightly more complicated than the classical metropolis Monte Carlo. It was historically the first simulation method. It's simply an application of Markov chain Monte Carlo to quantum mechanics. And you have a trial wave function, and you compute properties of the trial wave function. And it's based on the variational theorem. That's why it's called Variational Monte Carlo. Basically, you assume that there's a trial wave function. And I've switched the notation a little bit here. Capital R means the quantum degrees of freedom, which in your case, it's always going to be the electron position, right? And A, after the semicolon, are variational parameters. There could be many of them. At this point, they're just general function, right, that you vary. And the variational theorem, or Rayleigh-Ritz principle, is if you compute this ratio of expectation values, that is, H is the Hamiltonian, and you have this trial wave function, and so this is the expectation of the Hamiltonian, and divided by the normalization of the trial wave function. You might wonder why we have this normalization. The reason is the kind of wave functions that we use are not normalizable in a simple way. I mean, they're normalizable in the sense that this expectation value exists, but we don't know what it is analytically. That's where we differ from, say, density functional theory or Hartree-Fock. There, if you have a Slater determinant, you can compute the normalization integrals. You do compute them. You normalize the orbitals. But we deal with correlated wave functions, and you can't do that analytically. So that's why we have a ratio here, right? So the variational theorem is that this ratio is an upper bound to the exact ground state energy. And variationally, what you would do would be varying, choosing A, these parameter set, in order to get the best upper bound. Okay? Now, if in fact the variational energy equals the ground state energy, that means you've actually solved the Schrodinger equation. But of course, we don't normally expect that to be true, that we can't solve the Schrodinger equation for many-body systems. Now, we introduced something in quantum Monte Carlo called the local energy of the trial wave function. And this is defined as the Hamiltonian acting on the variational wave function divided by the variational wave function. And so this is a function of the electron positions. And this is why we call it the local energy, although that's what we always have called it, and so the name is stuck. But it is really more like the residual energy. It's the error of the trial wave function in a way. Okay, what would happen if their trial wave function, this psi here, was an exact solution? Well, then H psi would equal E psi, and the psi's would cancel out, and your local energy would be the ground state energy. So it would be a flat function, right? So maybe illustrating this over here again. If this is R, which is the many-body electron positions, and this is the local energy. And normally, well, if you have an approximate trial wave function, your local energy varies with electron position, right? If you had the exact wave function, it would be a constant. So this would be the exact psi, and this would be an approximate psi. So the local energy, the average value of the local energy is your variational energy. So variational energy is the integral over psi squared of the local energy, dr, and then normalized by psi squared. So that's why I drew this exact one lower than the fluctuations, right? So why is this so important? Well, it's because the variance of the quantum Monte Carlo depends on the fluctuations in the local energy. What are the fluctuations? They're this right here. This part is the variance, right? So you see the exact wave function is flat. It has zero variance. This means this is the zero variance principle, quantum Monte Carlo. As you wave function approaches the exact wave function, the efficiency, the variance goes to zero. So we can compute the exact answer with one sample if we had the exact wave function. We just have to sample one of these points if we knew we had the exact wave function. So this is, it is kind of important. You don't have this in classical simulations. If you're doing a simulation in water with classical mechanics, and you want to calculate like the energy, the internal energy of water, you have to do a lot of sampling. There's no way around that. But here we have a different procedure. We can make a better wave function, and then we can do fewer sampling points. Because we make a better wave function, and our local energy will look like that. And the variance will be less. We need less sampling in principle. Of course, we don't do that in practice. What do? We run just as long and we get smaller error bars, right? Which is what you want. Explain that. So here are the formulas. So this is what I just wrote. This is the local energy, the definition of the local energy. And basically, the variational energy, again, is the average over psi squared of the local energy. I think I had two brackets here because I wanted to emphasize that we have to normalize the wave function. That's why we have two brackets. So we always have a ratio like this. So in the last lecture, I talked about the Boltzmann distribution. Now we're going to sample psi squared, which psi is some analytic function that you have. And so how do we sample psi squared? Well, instead of, we move the electron coordinates and we see if psi squared goes up or down. If it goes up, we accept the move. If it goes down, we compare to a random number and accept or reject. So it's very similar. We take what we had e to the minus e over kt, we just replace that by psi squared. This was actually, we can say, quantum Monte Carlo had one of the birthplaces was right here, right? Bill McMillan was a graduate student at the University of Illinois, and 1964, he worked on what was called the Iliac computer, which was the supercomputer of the day, and he wrote this paper on how to calculate the energy of liquid helium. So he wasn't doing electrons, he was doing like Lennard-Jones particles, they're called. And what's the ground state energy? Does anybody know who his advisor is? His advisor is not on his paper. Well, that's good. A graduate student does path-breaking work and his advisor is not even on the paper. Does anybody know who his advisor was? Very famous physicist, the most famous physicist it should be in the world. John Bardeen, two-time Nobel Prize winner, invented the transistor, invented superconductivity. Anyway, but he didn't put his name on Macmillan's paper. Because I think winning 2 Nobel Prizes, you don't have to take credit for this too, right? Anyway, so basically, he just took the techniques that Metropolis had invented and said, we can make a good wave function for helium, and we can calculate properties of helium. And back then, I won't talk a lot about helium, but you know, there were still a lot of questions about why you have a superfluid helium, and you know what, and this is what it was in his paper, right? He just applied the existing techniques from one area, namely classical liquids, into quantum liquids, right? The same techniques, Metropolis, Monte Carlo. So this is a repeat, slightly more general. This is the variational wave function, and this is the variance. And you know, there are some conditions on the variational principle which sometimes people forget and make mistakes, but there are conditions. To get, the inequality is this, that is, you have to get an upper bound. You have to have a continuous wave function. You have to, it would be nice if the derivative was continuous, but that's actually not required. It'd be nice if all derivatives were continuous, but that's not required. You have to have the proper symmetry. Namely, if we're dealing with electrons, you have to have an antisymmetric wave function. Otherwise, you'll go down to the boson wave function. It has to be normalizable, and so both of these integrals have to exist, that they can't be. I gave you the example, what happens if an electron goes off to infinity? That would be an example of a wave function that's not normalizable, right? So these integrals, and this is something you don't use your quantum Monte Carlo to establish. You use, you know, you think about it, right? About whether these things are true or false. In fact, and then finally, there's a special quantum Monte Carlo condition, and that's called finite variance. Why? Well, I explained it already. Why do you need finite variance?
Use the central theorem.
Yeah, you didn't turn on your microphone, but I heard you. Namely, you have to have finite variance because you want to have error bars. If you don't have, what is the variance? The variance is this property right here, right? You see, oftentimes, a method that's perfectly okay in Hartree-Fock could have this thing diverge, that is, go to positive infinity. And what would you observe in the quantum Monte Carlo? Well, that was the graph that kind of disappeared the other time. But basically, if you're looking at the trace, this is again the trace. That is, we're looking at the local energy is a function of Monte Carlo time. Remember? This is what you see on a bad wave function. These spikes, they're called spikes, right? That's bad. You should try to understand those spikes. Why are they there? They should not be there. A good wave function will not have these things here. This means you cannot really trust the results if you have those spikes, because you don't know if the variance exists. And, I mean, why can those spikes be there? Well, it could be just a computer problem, namely a bug, or it could be because your local energy has some really bad places. That is, h psi over psi. I called this, but what happens if this thing goes along and there's some big place where the wave function is really bad, because the local energy is h psi over psi. So you're dividing by psi there. If psi goes to 0 and h psi does not go to 0, that means the local energy could go to infinity. And that could give rise to the spikes. So, it could well be, usually you get reasonable answers, but when you start computing error bars, you can't really trust the error bars. So anyway, there are some conditions on the variational principle. And, okay, so why do we do variational Monte Carlo? Well, quantum chemistry uses a product of single particle wave functions. That's called uncorrelated wave function, right? And by putting correlation directly into the wave function, you can get a much better description of an electronic system. And we're going to describe this. It's called Slater-Jastrow wave function that we'll talk about. And it puts correlation in there. But once you put in correlation into the wave function, you can't do the integrals that you do in Hartree-Fock or density functional theory anymore. And that's why you use quantum Monte Carlo. So we can use any computable function. Of course, I put it in quotes. I mean something special. What do we have to do when we do variational Monte Carlo? We do a random walk, and we move the electrons, and we have to calculate psi squared. That's what I mean by computable. We have to calculate it, and it would be nice if we could calculate it in a millisecond or something, right? Or some fast time. If it takes 1 day to compute it, then it's not very useful for quantum Monte Carlo. So basically, we sample R from psi squared using a Markov chain. We take the average value of the local energy. We've learned how to do average values. And then there's a bigger step, namely, we want to optimize the trial wave function. And actually, we'll have a special lecture on optimization, so I'll just describe this very briefly. One of the things is that the energy is second order in the errors. What does that mean? The energy that you calculate, this is the upper bound property, but it's usually very close to the exact energy because the second order. That means you make a deviation epsilon in your wave function, the energy is accurate to epsilon squared. That's what we mean. So if your wave function is accurate to 10%, your energy is accurate to 1%, right? Better wave function, lower variance. So this is a zero variance property. We're going to deal with complex wave functions later on. So, we often write these as the real wave functions, but actually the code deals with sometimes complex wave functions. And so the local energy is actually defined as the real part of this h psi over psi. Okay, here it's updated from what I showed you last time, but it's basically the same plot that we had. Everything's the same. The only thing that's different is we calculate psi squared, so you have a routine. Of course, all your computer time is this step right here, computing psi squared. Obviously, this would run at a gigaflop, except for you have to go off and compute psi squared. And that's a much slower operation. But everything's the same. You have to have a function that computes the wave function. And I didn't write down the averages, of course. So the average you want is the local energy. That gives you the variational energy. Okay, so the procedure that we use to move the electrons I won't repeat this later on, but basically, we use a Gaussian to sample the new electron coordinates. And again, capital R are the electron coordinates, and F is the gradient of the log of the trial wave function, is what I call the pseudo force. It's like the force that would be necessary to sample psi squared if you're doing molecular dynamics. And so this kind of pushes you in the direction of the trial wave function getting larger. So basically, you have, this is the old position R, and this is the mean position, the most likely position of R prime would be R minus tau times F. Tau is what's called the time step. This corresponds to delta that we talked about before. What was the role of delta? Delta was how far you move the electrons. How far do you move these electrons? Well, you move them like the square root of tau. And so, again, if you're working in atomic units, you want to move them on the order of 1 Bohr radius. So the tau would be on the order of 1 in atomic units if you're dealing with a hydrogen atom, for example. So that's on there. But what you want to do is you look at your acceptance probability, and you want to optimize your acceptance probability, right? But now we have a non-uniform T. That is, the probability of R going to R prime is different than R prime going to R. So we use that generalized metropolis formula, right? And in fact, this is the formula for acceptance probability. So you have the ratio of the trial wave functions, and then you have to compute now these forces, these pseudo forces, in the forward and the new position and the old position. I'm sorry, R is the old position, R prime is the new position. So the idea is you sample, you're at a given position R, and you calculate F. You sample from a Gaussian. That's a standard thing that you learn how to do, how to sample from a Gaussian. I guess I don't explain that, but it's a simple thing to do. And then you move to a position R minus tau times F, and then you have a Gaussian that has a width of the square root of tau, okay, and that's your new position. And then you calculate this acceptance probability, and what comes in there is the force at the old and the new position. Okay, and so that's all the work is in computing the forces. Okay, I'll explain a little bit more about this update formulas. There's one thing I didn't describe about metropolis. You don't have to move, you have a lot of freedom in how you move, and we usually move electrons one at a time and not all together. This formula would suggest that you move them all together, but you usually say, let's move electron 1, let's move electron 2, let's move electron 3. Why do you do that? It's more efficient to do it that way because your wave function can be broken down into updates where you move electron 1 and you only have to calculate properties of electron 1. And so, and combined with the fact that if you move, say, 1,000 electrons simultaneously, your probability of getting accepted would be very small because with 1,000 electrons, you're almost certainly going to move into a bad place because it's like back to the drunkards. If you have one student wandering around drunk in town, it'd probably be okay. But if you have 1,000 students, the chance that one of the 1,000 students gets into big trouble is almost certain, right? So it's the same with the electrons. It's better to move them one at a time and accept or take care of them one at a time because each one only takes 1/n of the work of moving all of them. So it's faster to do it that way. It's more efficient. So generally, it's around 10 electrons that is a crossover of the efficiency.
Sorry, lambda again? Lambda
Oh, lambda, I'm sorry. In atomic units, it's 1. Lambda is h bar squared over 2m. Okay. I'm sorry. My notation wasn't explained. Does everybody know about periodic boundary conditions? This is something that, well, we'll explain some of the like. Okay, if you're doing a condensed matter system like a solid, then you don't want a surface. You don't want to do a little crystallite with a surface. What you do is you put them on a torus mathematically, periodic boundary conditions, and you have to compute the distances in periodic boundary conditions. And so this is what we call the minimum image convention. This is the minimum distance between two particles. And it's important that we treat the wave function like that. And we'll come back to this when we talk about Coulomb forces, but there's something called the Ewald potential. And I think Lucas, you're going to talk about this, or somebody about Ewald. Okay, so I won't talk about this. So there's special techniques that you use. This is actually part of the complications when you write a real code, is to deal with when electrons come to the end of the periodic boundaries, they have to map them back in, and you have to calculate distances in a periodic space, okay? Okay, now the important part of variation Monte Carlo is what do we use for the trial wave function. The formal requirements I mentioned already before are continuity, finite variance, anti-symmetry. Now what's used in Hartree-Fock and density functional theory would be a Slater determinant. And that's actually the place where we start. We have a Slater determinant. And that will give you the anti-symmetry. But if you just had a Slater determinant, there would be no point in quantum Monte Carlo, because you can do that with much more efficient techniques with a simple Slater determinant. Now, there are people that expand in a basis set like multi-determinants, but that doesn't, again, there's no point in doing quantum Monte Carlo if you expand in determinants, and that's a very slow expansion. The way I think about how you improve the wave function is based on this local energy, based on a local energy argument. This is the local energy, I explained before, the exact wave function would have a constant local energy. Now, what does the local energy look like for a constant wave function? So psi equals 1. That's called let's just do a hydrogen atom, for example. The local energy is h psi over psi, and we're going to deal with the usual non-relativistic Schrodinger equation. So this is 1/2 del squared psi over psi plus v, the potential energy. So if we're doing a hydrogen atom, the local energy, this factor would be 0 if psi is equal to 1, right? The derivative would be 0. So you just have the potential energy. So your local energy would look like that, right? It would be just the potential energy. This is not a constant, right? So what does the wave function look like? Well, this is the hydrogen atom wave function. So the correct wave function, of course, is e to the minus r in the right units, right? That's the hydrogen atom wave function. And the local energy would be a constant, right? So, this wave function looks like this, right? So we want to add in a factor, which is like e to the minus r. So what about now, instead of dealing with one electron, we have many electrons. Our potential energy is the sum of 1 over Rij, the electron-electron interaction. This is the electron-electron potential energy, right? And this, if we use Hartree-Fock to solve the electron ion potential, then what we have left in our local energy is the electron-electron interaction. And this is a singular function too. When any two electrons get close together, this goes off to plus infinity. So this is the term we want to fix in the local energy. And how do we do this? We do it by what's called a Jastrow wave function. So we want to control the singularity in at small r or R12 and leads to the cusp condition. We also, and you can do that based on this local energy idea. That is, if the local energy is this right here. Basically, the local energy argument is that if two electrons get close together, we can write down the local energy for just that pair of two electrons. And we're left with a Schrödinger equation for those two electrons. And we can solve that Schrödinger equation just like you do for a hydrogen atom. And you end up with a wave function, which is e to the minus u of R12. And that u function, that's called the Jastrow factor, it looks like this, right? And so this is the way we can take care of the electron-electron interaction by putting an extra term in the trial wave function. And this is the singularity at small r. And that leads to what's called the cusp condition. The cusp is this thing right here. Is the fact that there's an exact relation between the slope of the wave function at R12 goes to 0, and there's an exact derivative, and that's the cusp. You know that for any exact wave function, that it has to come in to the origin with a given slope. And that's what's missing in Hartree-Fock. Hartree-Fock, you don't have this function in there, so you have 0 slope. You can also do the same thing at large r, and there's something called plasmons in a charged system or charge oscillations. And that the local energy argument, or looking at the local energy, tells you how the wave function should behave when two electrons get far apart. And there's something they call the Feynman-Katz formula, which kind of pulls all this thing together and tells you how to, if you have a given Hamiltonian, what terms you should be putting into your trial wave function. And I'll describe those a little bit.
Excuse me, I have a question. What's the x-axis there? Is
here?
Yeah.
Here is just R12. R12. The distance between two charges, two charged particles. Here I was referring to the distance between an electron and a proton, or an ion. And here I was referring to the distance between two electrons. It's the same idea. Okay, and this is one of the, just to remind you of the two-electron ground state. If we have two particles, the total wave function has to be antisymmetric. If we assume that the spin function is a singlet like this, then the spatial wave function is symmetric. And if the ground state is non-degenerate, we can assume that the wave function is real, positive, and symmetric. And you can prove this, basically. So in other words, for two electrons, this would be like, for example, a helium atom, two electrons. We can assume that the wave function has this form, where u is a real function that is positive. We refer oftentimes to this as a bosonic problem. That's why, because quantum Monte Carlo this is really the simplest thing you can do in quantum Monte Carlo is a helium atom, right? And you can assume the wave function is this form, and this U factor, it has to be symmetrical in the electron coordinates. These are the 2 electrons in a helium atom. It wouldn't have to be a helium atom. It could be any 2 electrons at any other external potential. It would have to have this form. And so, I mean, the important thing is that this wave function is a positive quantity, so it can now be sampled like a probability distribution. But U, remember we're doing variational Monte Carlo, is a variational function. Namely, we know exact properties of it, but we want to put in parameters and vary the parameters to find the best description of it. Here is an example for a hydrogen molecule. Again, a hydrogen molecule is a 2-electron system, and these are sort of uncorrelated wave functions. This is a restricted Hartree-Fock would be you take 2 molecular orbitals, and these are the 2 protons, A and B, and the 2 electrons. Well, I'm sorry, this is 1 electron here. This is distances between the 2 protons. So the wave function has to have this form. And usually, this is a good wave function. It's called a Heitler-London function, where we have an orbital on A plus an orbital on B times an orbital on B plus the symmetric combination. So the type of wave function that really works well for a hydrogen molecule is this sort of single electron piece, which consists of 2 determinants, if you like. They're not really determinants. They're just 2 products and 2 terms. And then what's called a Jastrow-like piece or a bosonic piece that correlates the electron 1 and 2. And this is this U function. And basically, all you know about this U function, you know the cusp condition, what happens when 2 electrons get close together. This is the space, right? You have two electrons. And the cusp condition gives you the derivative of U when they get close together, and it tells you what happens when an electron gets close to a nuclei. Now, the correlation energy, that is the energy that's missing from this wave function, is 1 electron volt. I'm switching to physics units. That's like 10,000 degrees. That's really a big energy. If you do the simplest approximation to U, that is, you just assume that U is a function of R12, a spherical Jastrow, you recover 1.06 EVs. That is the simplest approximation that correlates these 2 electrons together. So you're getting sort of 95% of the correlation energy that would be missing, say, in Hartree-Fock or density functional theory. That's why we use variational Monte Carlo, just by adding a really simple function. We know that it's not perfect, but a simple function that has this cusp in there would give you 95% of the correlation energy. It basically keeps the electrons from being at the same place, right? Because they're in a spin singlet state, the determinants don't keep them apart. And so you have to add this, you have to put in this kind of function. So this is the simplest Jastrow problem. That is why you see. This is U is what we call a Jastrow wave function. Maybe I'll skip this here. Probably, how am I doing on time here? Oh, we have 15 minutes left. Okay. Well, this is maybe I'll explain it. Basically, the Feynman-Katz formula is really a nice formula. It kind of tells you how you go from the local energy to the exact wave function. And I was explaining before how you can use the local energy over here to the singularities to figure out what terms to put in the wave function. And this is an exact formula, but as all exact formulas, you can't use it in detail. You just use it to construct ideas. And basically, it says the exact wave function is given by your trial wave function times the average value over certain kinds of random walks of the exponential of the local energy. And so basically, you want to find out the wave function at this point. At this point, you start out random walks from that point, and you average the local energy. This is, in fact, what we're going to do in Projector Monte Carlo tomorrow. But what we're using it for now is we're saying, let's start out with a Hartree-Fock wave function and use the finite, use the Feynman-Katz formula. As I explained over here, the local energy, if you start out with a uncorrelated wave function, is just the bare potential. So that means if you want to improve an uncorrelated wave function, you just put something in the wave function which is like the average value of the potential energy of the term that's missing. And in this case, in the case of a Hartree-Fock wave function, what you're missing is 1 over Rij, the electron-electron potential. And so you want to average the electron-electron potential over random walks. That means you want to smooth them around. And basically, you can show analytically, basically, that you want to take a smooth potential energy. And that leads to a Jastrow wave function, basically. And so basically, this is what Macmillan did. He didn't have to worry about fermions, but he used just a Jastrow. And so the wave function is just the product over pairs of particles of e to the minus u, where u is a variational function, and it's going to be like a smooth potential energy. And the question is, what is the local energy of this wave function? And this would be, you can show that this is the local energy of the wave function. And so you have the bare potential here, and you have del squared of this Jastrow factor, and you have something called the gradient squared, the gradient of the trial wave function squared. This is the local energy. Why do you have these two terms? That's because you have an exponential here. So when you take the first derivative, you pull down a u. You take the second derivative, you have two terms. You have this term and that term. Now, v of r diverges as 1 over r. How should u of r diverge? And this is basically, the argument is you want your local energy to be constant, so you want the singularity here to be matched with this singularity here. This is the most divergent piece. And that gives you this cusp condition, namely the derivative of u at the origin is minus 1/2. So that's the famous cusp condition, the Cato cusp condition. And this is the argument why it's true. Now, if you're dealing with fermions, you use this so-called Slater-Jastrow wave function. You have a determinant. This is for plane waves, that is like in a fluid electron gas I'm going to talk about. But you could have orbitals here instead. And then this is the Jastrow part, so this puts in the correlation. Now, I'm going to talk about, I guess we talk about finite size effects later on. But with wave functions, I talked about when you're doing a simulation, you have periodic boundary conditions. But with quantum mechanics, there's a new feature in periodic boundary conditions. If an electron goes out of the periodic box and comes back, it can pick up a phase. That's called the twist angle. All the electrons have to pick up the same phase, but that's what this theta is. And the reason that you do this is because it's equivalent to integrating over the Brouwer zone in a solid state calculation. By doing that, you cut down finite size effects a lot. And we'll talk about this later in the week. And those are called, twisted boundary conditions, this theta. So you end up with a complex wave function. But anyway, so I'll explain that later. There's a new feature of quantum Monte Carlo as opposed to what Macmillan did and what classical Monte Carlo is you have to deal with determinants, misspelled there, but okay. You want to sample psi squared, and psi is a determinant times the Jastrow factor. The Jastrow factor is just like a classical potential. There's nothing new here, but the determinant is new. Okay, so you have to sample psi squared. Actually, this was my project in graduate school, is to do this. And, we had all sorts of worries like, psi squared is positive and negative region. I mean, the determinant has positive and negative regions. Maybe we're going to get stuck on one side. It's just like somebody asked me about a double well potential. Maybe you get stuck because the wave function changes sign. It has so-called nodes. Well, actually, there wasn't anything to worry about. Sometimes you should just proceed and not worry about things, and actually you don't get stuck. But one of the things that I learned is that there are these formulas in linear algebra that allow you, when you move one electron, allow you to update the determinant, so you don't have to recompute the determinant every step. When I started out, we had to compute the determinant every step of the random walk. Now, what we learn is so-called recursion formulas that say when you change one column of your Slater determinant, you just update the inverse. And that's much faster, and it's something that's done really fast on computers because it's a simple dot products that you can do really fast on the computer. And those are so-called Sherman-Morrissey formulas. And this is, it's a linear algebra trick that allows you to change the inverse when one of the columns change. And it changes the complexity. A determinant is order n cubed operations. The update formulas are only n squared. But they're not only n squared, they're really small, fast n squared, because they're just dot products, and there's Blaz routines that do them quickly. Right? It's the kind of thing that computers have been optimized to do. But of course, it is the dominant calculational time if you have 1,000 electrons. But if you're doing 100 electrons, you don't. It's really fast. So normally we talk about quantum Monte Carlos, we're dealing with real wave functions, but actually very often, nowadays we're switching over to do more complex wave functions, but you can work, oftentimes you can take a wave function that's complex, like e to the I k dot r, and break it into two real wave functions. And you get the without increasing the energy, you can just deal with the real wave function, not the complex ones. Sometimes you have to deal with complex wave functions. It's no problem in variational Monte Carlo having complex wave functions, and it's actually more fundamental to do it this way. It's the same with spin. We often, in quantum Monte Carlo, we assume that the electrons are up spins or down spins. They're just like two different kinds of electrons. This is actually, it's kind of an approximation. It's a simplification, and it obeys the variational principle, but you can sometimes get lower energies by not doing this. And of course, when you talk about magnetic properties, you have to be really careful about doing this. We normally don't have an explicit magnetic field in our calculation. We just deal with the polarization of the system, that is the number of electrons, up electrons minus down electrons. So we'll talk more about this later, but this gets kind of more complicated to deal with the spin. So in extended systems, we normally use an SC representation, so we have a fixed number of up and down electrons. And we anti-symmetrize only among electrons with the same spin. So this is kind of a preview of more realistic trial functions. We often use LDA or DFT, derived pseudopotentials, to get rid of core electrons. We take orbitals from other methods. For example, we take Gaussian orbitals from like games or DFT. Plane wave codes give orbitals for extended systems. We use quantum espresso and some other codes to get the Slater determinant. We multiply by a Jastrow function, and we can include other terms. And basically, we'll talk more about this later in the week, exactly how you treat realistic trial wave functions. These are the important points, anyway. Now, what about this U factor? Well, HEG, by the way, is a homogeneous electron gas. If you just have electrons without any nucleus, nuclei, or ions, we can expand the best Jastrow factor into a short-range part and a long-range part. We can make sure that this short-range part goes to 0 at the edge of the box. We need to do this to satisfy the variational theorem. U of R must be continuous with the continuous derivative, and so we want this USR function to be continuous, and we want to impose the cusp condition, exact value at R equals 0, and we want it to make it be a smooth function. So what we do is represent it by a spline, namely a piecewise cubic polynomial. And the region L is the size of the box, the supercell, if you have an extended system. So we want to represent it by a piecewise continuous function, and there are what are called knot values at certain values, like 10 different points, like you go from 0 to 0.1 or 0.1 to 0.2, 0.2 to 0.3, and you would have polynomial coefficients, that is cubic polynomial coefficients, in each of those regions, and those would be your variational parameters. So that if you have m knot values, the total number of unknowns is 2m minus 1, and those are basically your variational parameters. So that's an arbitrary function, and so like your Jastrow would have, if you have 10 knots, would have maybe 20 parameters, and then you can also add a long-range piece like this, where this k is restricted to be in the reciprocal lattice of the supercell. And these are what we call long-range Jastrow, and we might fix those with an analytic argument, or we might consider them as variational parameters. So you would try to optimize that. I said that for homogeneous electron gas, but that applies to real materials too. I mean, to silicon or whatever you're doing. These can be your Jastrow parameters, your variational parameters. So this would be how you represent the basis set to represent an arbitrary correlated function. Now, here is taken from Macmillan's paper, the optimization that he did for his trial wave function. So this is his variational parameter, and this is his energy. And so this is the simplest possible way to optimize things. You just vary the variational parameters, you fit it with a curve, and then you say, this is the best wave function you can get for helium. Okay. Now, the one thing you can do is better, it's called a reweighting technique, is you sample from some probability distribution for some parameter set A0. You sample configurations, you make like a database of configurations out on your file with them, and then you figure out how the wave function would change if you changed A0 to be some other parameter A, and how would the energy change. And basically, this is how the variational energy change. Basically, it becomes a weighted sum. And the weight is the ratio of the wave function from what you sampled to what you want it to be, the new value. And so this is the weight, and basically you have a weighted sum, and then you just give this weighted sum to a standard numerical procedure that would minimize this energy. And it just goes downhill, it forms the steepest descents. There's various minimization algorithms, and that would return the best value of A. And that would return the least upper bound for the ground state energy in this function space, whatever function space you're describing here, like the best Jasper wave function. However, this procedure, this is what I always used to use, but it has problems. The problem is that away from A0, the statistical accuracy gets worse, it declines. So your error bars grow, and so basically the procedure can be unstable. And so it can fall into a hole, basically, and give you nonsense. But anyway, this is one of the procedures that you can use. But a better procedure, basically, is a more modern procedure, is you essentially calculate the gradient of this local energy, and you go off in that gradient, and you do another variational Monte Carlo calculation. And so this is what you'll learn about later in the week. I described this, but I think we want to get to lunch here pretty soon. I want to say that energy by itself doesn't tell you very much. This is a kind of a mistake that people make, that they work only looking at the ground state energies. However, with variational Monte Carlo, other properties do not have an upper bound principle, and they're not nearly as accurate. The other things that you might want to compute are things like the pressure, the density, the pair correlation, order parameters, how to tell a liquid from a solid, and like the momentum distribution. And there are procedures to calculate all of these things. But they tell you a lot more about what's going on in the system than just the energy, although the energy is the thing that's computed most accurately. The pair correlation function is really important. That tells you if you put an electron down here, the red and the blue are supposed to be up and down electrons. So this is like a ferromagnetic system where the red electrons and blue electrons are coalesced together, I mean, in regions of upspins and downspins. And so this is what you would find out if you put an electron in here, you know, is it surrounded by electrons of its same spin or different spin? From the pair correlation function, you can calculate all pair quantities like the potential energy and so forth. The static structure factor is its Fourier transform, and it's the thing that's measured in neutron and X-ray scattering, and it can provide can be used to see the state of the system, whether it's a liquid or a solid or a gas or so forth. And here's an example for the electron gas. This is the pair correlate. This is the probability that this is the distance between two electrons, and so this is like electrons, and this is all electrons, and it shows you that this is a so-called correlation hole around a given electron. The other electrons avoid being around there, and this is a quantitative measure of that, of the electron-electron correlation. And this is its Fourier transform in K-space. This is what you measure in a scattering experiment, the so-called structure factor. And it's shown what free particles are like and what interacting electrons are like. Okay, so this is the kind of thing that, well, that you want to compute and look at to understand, correlation. I think I'll skip over that. This has to do with the solids that I don't think we'll talk about this week. Here's a momentum distribution. You know, classically, the momentum distribution of any system is a Maxwell distribution, a Gaussian. Electrons, quantum mechanically, are very different. And what you get in electron gas is you get the so-called Fermi function, which you all learned about in statistical physics. This is the Fermi, well, the Fermi function would be 1 occupied orbitals and 0 for outside of the Fermi wave vector. This KF is the Fermi wave vector. This is for an electron gas. And what happens when electrons become correlated? Well, then you go to these curves, right? This is a realistic electron gas, or a simple metal like aluminum or whatever, the momentum distribution, all of these electrons are not, these states are not occupied, but you get the interaction causes some of these states with K less than KF to be unoccupied, and it pushes them up into these states here. So this is a so-called quasi-particle strength. And we computed these. You can compute these in quantum Monte Carlo. I'm not sure, we don't have an exercise on doing that this week, I guess, the momentum distribution. But anyway, this is kind of what we can compare with scattering experiments, showing the effect of correlation on the momentum distribution. Well, no, maybe we should just, okay. I wanted to talk about their wave functions beyond the Jastrow. If you use this local energy argument and you plug in the Jastrow wave function, this is the Jastrow wave function right here, where you have a Slater determinant and the Jastrow factor, and then you try to iterate this local energy argument, you get this as the local energy of the Jastrow wave function. And this has two new terms. And remember, my Feynman-Katz argument means you're supposed to smooth out these two terms and make an even better wave function. This term is the square gradient of the Jastrow wave function. And this is what we call a three-body term. It correlates electrons 3 at a time. And this part is called the backflow term, and it puts correlation into the Slater determinant. The Slater determinant itself is an independent electron object. But if you correlate the coordinates that go into the wave function, that's called a backflow. And this says how you should correlate the electrons. And this shows, and basically, the Slater determinant for the electron gas is a determinant of plane waves that are occupied up to the Fermi wave vector, e to the ik dot r. And basically, if you want to put in correlation, it becomes a same kind of determinant, but the arguments of the plane waves are now dressed electrons. That is, the electron coordinates become the bare electron coordinates plus something which is like a force acting on the electrons. And this picture here shows you, well, this shows you what the best backflow functions look like. So we optimize these Jastrow functions. And this shows you how much energy that you're recovering in the electron gas by adding in backflow. So 0 means the Slater Jastrow wave function, which already has 95% of the correlation energy. When you add in the backflow, it's like you get 99.9% of the correlation energy. So 0 means Slater Jastrow, and 1 means the exact wave function. And so by this three-body, these other things are, what if you add in the three-body, what if you add in backflow by itself, or what if you add in both? You see, you recover most of the energy by adding in backflow. So backflow works really well for electron gas, and actually it's in QMC pack. You can try it out for solid state systems. You can get something improved wave function beyond Jastrow. And well, anyway, so this shows you, well, this is the same kind of graph. It shows you at one particular value of RS, as you go from, okay, Hartree-Fock would be up on the 3rd floor, and then you come down. This is the energy of a Slater Jastrow wave function, and then this is the backflow wave function right here. And this is where we think the exact answer is down here. So this is my last, well, this is the last graph. I have one more summary. This is a conceptual diagram, which is actually true for hydrogen. This is the log of computer time. So this is 1,000,000 hours here, or seconds. This is 1,000,000 seconds. Arbitrary units. This is the error in atomic units. And I combine together two things, statistical error and systematic error. So you take a simple trial wave function and you run it longer, and your error decreases as the square root of computer time. But eventually it's useless because you're just looking at the error, your systematic error in your trial wave function. So you make a better trial wave function and you get both a lower systematic error and a lower statistical error. And but you have to run longer to achieve that because maybe your wave function is worse. I'm sorry, your wave function is slower, but you can get better. But variational Monte Carlo is not quite good enough because this is where we want to be with applications. That is, we want to get things which are like 10 to the minus 3 atomic units accuracy. And variational Monte Carlo doesn't always get down into there. And you also don't want to run too long. You can have only so budget. So this is where the applications are. Okay, so we have so the variational method is very powerful since you can use any trial wave function. And you learn directly about what works in the trial wave function. If you put an extra term in and your energy and your variance go down, that's the right term, right? You won't have any sign problem. We haven't learned about the sign problem yet. The scaling is almost classical. We can do thousands of electrons, okay? But some of the problems, the optimization is time consuming. The energy is insensitive to order parameters. So that means, for example, there's certain parts of the energy that fluctuate more, but that may not be the part that you're interested in. Like you may be interested in like the energy to magnetize the system, but maybe that's not, but you find that simple states are favored over more complicated states. A ferromagnetic state is easier to write down a wave function than a paramagnetic state. So you're going to get a bias towards the ferromagnetic state, and you're going to get the transition in the wrong place. It's difficult to find out how accurate the results are. Non-energetic properties are less accurate, like looking at the scattering function is less accurate than the energy. And mainly, the problem is there's a famous, used to be a famous acronym in computer science called GIGO, garbage in, garbage out, right? If you're going to get an answer, you're going to get an answer, a variational answer, but if it's not the right form of the wave function, you don't know it, right? You just get an answer with an error bar. What goes into the trial wave function comes out. So we need a more automatic method, and that's projector Monte Carlo. Projector Monte Carlo starts with the variational Monte Carlo, and then just by applying more computer time, you get a better answer. Not perfect, but better. And so that's what we're going to learn about tomorrow morning, is the projector Monte Carlo. But you have to understand variational Monte Carlo because that's the place you start from. And, so I'll stop there.